I don't even.
Okay, so let's
I understand it, but.
talk a little physics. Let's talk kinematics for a second. There's some questions come up on the assignment that have to do with a little bit more than maybe what we talked about. I gave you some definitions of, some really brief definitions of velocity and acceleration and position, but we gotta go maybe a little further than that. In order to be able to tackle the really fun kinematics problems, you gotta be able to do a little more than that. So let's come up with some definitions. First of all, let's talk about vector quantities. Okay, so I'm gonna write this down. You can write this if you want, but this will be on YouTube, of course. Okay, vector quantities. Are you familiar with that terminology? Physics people. What are the characteristics of a vector? Direction and magnitude. Good. Okay, so it's got both a direction and an amount, right? Vector quantities. We'll talk about some vector quantities. What's in contrast to a vector? You know what the other quantity is called that doesn't need a direction? So vector quantities versus scalar quantities.
Oh, I know, yes. That was actually my third guess. What was after Ray?
So vector quantities need both a direction and a magnitude. Scalar quantities only need a magnitude. So give me an example of a scalar quantity. Mass, sure. That's a good one. Or temperature, or something like that, right? Where it's just a number. Vector quantities, direction, and magnitude. So first one, here's the game we're gonna play. We're gonna look at some one-dimensional kinematics. Oh, it is a great game. Look at some one-dimensional kinematics along the front of the room. So we're gonna say, I'm just gonna walk back and forth along the x-axis up here, and we're gonna tell a story. The story that we're gonna tell is pretty boring in one dimension maybe, but we can give it a little flavor here and a little pizzazz if we graph it. So here's our graph. So there's the x-axis, and we're going to look at this. Actually, let's do it this way. We're not going to do it that way. We're going to look at it where this is time, and this is my displacement along the x-axis. Okay. I probably should have picked something different. Instead of x is bad. That's a little confusing. We'll call it s for displacement. Okay. And a lot of times that's the variable we use for displacement is s. And typically, have you seen that in physics? Put a little vector hat over it, indicates a vector quantity. Okay. So s of t is our position function. Now, if I'm just walking along the front of the room, so let's say this spot right here is the starting line. That's the displacement of 0. So what's my displacement, or what's my position now? Not displacement, sorry, position. About, say, 2 meters-ish, something like that. Positive 2, agreed?
Yeah.
I walk back this way now, I'm about -1, okay, yes. Something like that. Now, the scalar equivalent of position is like distance, something like that, right? Or maybe that would more equate better with displacement. Let me tell you what displacement is. I think it really works more interchangeably with that. So displacement is just a change in position. So if I start here and I end here, my displacement is +2. But if I then take a step backward, what's my total displacement now? It's only +1, right? Because even though I've gone through a distance of 3 meters, my total displacement is only 1. And if I took a trip like this where I walked clear out here and really accelerated, slowed down, and came back, my net displacement is 0. Okay, good. And so when we define things like some average quantities, displacement delta S that just equals S, we'll call it S final minus S initial, something like that. Okay. When I want to define something like average velocity, Okay, so that's all displacement is. Displacement is just a change. Whenever we talk about a delta something, it's also always the final amount minus the starting amount. So displacement is just a change in position, where we end up minus where we started. That's related to average velocity. So if we want to define something like v bar, the bar means average. Okay, so average velocity is just going to be change in position, known as displacement, divided by change in time. Okay. So if I start here and I walk out, let's say to here, I walk out here 5 meters, and I walk back 5 meters in a period of 10 seconds, what's my average velocity?
0.
0. Yeah, see why?
Yeah.
Because I haven't gone anywhere, right? Okay, now what's my, right? That's a little weird. My average velocity is 0. Now what's my average speed? Because speed's different. Speed is total distance over total time, and then it would be 1. Because I've walked a total distance of 10 meters. Speed's a scalar quantity. It's always, or excuse me, distance is a scalar quantity. It's always positive. As you walk in any direction, you just accumulate distance, right? So that would be 1. Okay. So that's average velocity. Now, what this is non-calculus stuff. This is the kind of stuff that you would talk about probably in your algebra-based physics class, your non-calculus-based physics class. But what we add to the picture here, and so this has nothing to do, this is just good physics, but it's not calculus, right? Where the calculus comes in is when we talk about, instead of these macroscopic changes, these average velocities and total displacements, we talk about instantaneous quantities, right? So if I start here and I begin walking in this direction, what does my speedometer say? With the added dimension of, I got direction associated with it also, right? If my speedometer reads 1 meter per second and I'm walking in the positive direction, then my instantaneous velocity is positive 1, right? If I turn around and I walk backwards with a speed of 1 meter per second, well, now it's negative 1 because it's going, right? Okay, so that's what we're getting to is the instantaneous stuff. That's where the physics comes in. Okay, if we look at some graphs of what these really interesting trips along the front of the room look like, I want you to maybe just describe to me, what's this? So if I start, so if this is position as a function of time, and this is my graph. I want you to think about that for a second. See if you can tell me, what story does that tell? Fascinating.
It's triangle. 90-degree angle.
So what is this? What is this point right here telling me? Well, the coordinates to that point are 0, 0, right?
Yes.
So what's that telling me?
Starting with nothing.
Okay, I'm starting at the starting line. When I start the stopwatch, I'm at the starting line. Okay? This point right here, which is, I don't know, let's just say that's at 5. What's that telling me? Okay, maybe I took 5 seconds. Well, I've moved some 5 meters or 5 yards or whatever in how many seconds? 5, because t is measured, let's say t is in seconds and s is in meters, right?
Yeah.
So when t is 5, s is 5.
Yeah.
And then back down here, maybe we're at 10, 0. Going back to my starting point. Okay, but it actually tells a story in between, too. What can you tell me about this segment right here? Okay, moving in a positive direction.
Yeah.
And what can you tell me about the nature? Which of these two things describes my movement from here to 5 meters out? Here's exhibit A. There's exhibit A. Or here's exhibit B. Which one is it? Which one is it, A or B? How do you know? How come? Oh, okay, good. So what's constant about, mathematically, what's constant about that? The slope, right?
Yeah.
Okay, okay. And what is slope, right? We know slope is rise over run. So my slope up here is just going to be change in position, right? That's change in, right? Change in y, only now it's an s, over change in t. Well, what did we say that was? Displacement. Change in position is just displacement. Displacement over time is, remember what we said that was? Yeah, it's just average velocity, right? So my average velocity here is going to equal. It looks like it never changes. The slope is constant the whole time, and so I've got my cruise control on, right? I'm moving at constant velocity in a positive direction, and then I just change, I change and start bounce off a wall or something, and I'm heading back with negative constant velocity. Okay, make sense? Okay, let's make this a little bit more interesting. That's pretty boring. So,
That was very exciting.
so now what if I do this?
Okay, it's gonna be a curvy thing.
That's more realistic. If I actually, if I did this, it would kill me. So this is, I'm gonna do this instead. And maybe you can tell me why that would be so dangerous here in a second.
Oh.
Yeah. Okay, same things. We've got displacement and time. What's going on there? Okay, yeah. And here's where a little calculus comes in. Right now, calculus becomes important to us because if we look at the slopes of the tangent lines to that curve, the slope of the curve, remember the slope represents velocity, right? And the slopes to the tangents of the curves, which are always changing, that's really just instantaneous velocity. So we're starting off with a tangent line with a slope of 0, so I'm at rest. But then as I move along, that's getting steeper and steeper, so I'm accelerating and picking up speed. What's going on between, say, here and there? Okay, so we could call that deceleration, right? I'm slowing down. In what direction am I moving? Still moving forward in a positive direction, but just decelerating, right? At the top is where I turn around and I start moving backwards, right? Picking up speed in the backwards direction and then slowing down, right? Get the idea?
Yeah.
Okay. So what if I wanted to look at my acceleration over that time period? What's that going to look like, do you suppose? Any ideas? This is, and I'm kind of jumping the gun on this. Just we're going to spend a lot of time. This is really important thing to be able to do, be able to relate the curves of functions and their derivatives. Because if we go back to what we talked about the other day, remember what we said. Velocity is just equal to, if I do v prime of t, v of t is just equal to s prime of t, right? Let me erase that.
Yeah.
Right?
That's, yeah.
And we just did that. We just drew in the tangent lines. So the slope of this blue curve gives us the value of the velocity function, right? And then if we went one step further with that, we said that acceleration, equals v prime. Okay, so what might a velocity curve look like? If we wanted to draw the velocity here, what do you think's going on? We're starting, and let's assume that it's the simplest possible velocity function. Oh, we're getting to that point. Okay. Okay, we'll draw this curve and then we're out of here.
All right, yeah.
Okay, so let's assume this is the simplest possible velocity curve or function that we could create. We're starting with 0. It's gradually picking up positive velocity to some maximum. What's the velocity going to be? And then you tell me what's going on. What's happening to the slope here? It's picking up speed. What's the velocity going to be right there?
0.
Oh, okay, good. You got that. It's 0, right?
Yes.
Because the tangent is horizontal.
Yes.
Okay, so it picks up to some maximum about right there, let's say,
Yeah.
and then it kind of tails off to 0.
Yes.
And then what's happening to the velocity over here?
Down.
It's going down, it's getting negative, isn't it?
Yes.
To some negative maximum. And then it begins to kind of tail off again towards 0. So if I superimposed a velocity curve over the top of this, what do you think it's going to look like? Start here. And let's draw it with just straight, I'll give you a hint, straight segments. There's no curvature to it at all. So something like that. Because isn't that the maximum we said was at this time right here? Whatever time that is, that's where it's at its peak. And then right here it's at 0. Does that make sense?
Yeah.
Okay. But then it gets negative, so it keeps going like that.
Yeah.
See what's going on?
Yep.
And then it goes back to 0.
I'm totally seeing this.
Right? So the green, you get where we're going?
Yeah.
So the green function is the velocity graph, whereas the blue function was the position graph. Now, if we went one step further and did acceleration, it'd be a piece of cake. The acceleration would be a super easy one to graph because that's just a constant positive slope, isn't it? And remember, the slope of the green graph is going to be the value of the acceleration graph because acceleration is defined as the derivative, the slope of velocity. So if I drew the acceleration graph, wouldn't it just look like some positive constant until we get there, because that's a positive slope? Then it's discontinuous and it becomes negative, right? All the way over to here, and then it becomes positive again.
Yes. Totally see it.
You get the idea?
Yes.
Okay, that's actually pretty good work for today. We'll pick that up tomorrow and go further with it. I'll get you on the left. Let's go.
I know.
Actually,